Okay, so yeah, I guess the screen is visible, right?
Yes, ma'am.
Okay. So just a heads up, your assignment, your final assignment submission is due on this Sunday, the 25th. Okay, so just a reminder about that. And yeah, so we were looking at Lagrangian duality yesterday. So where we saw how to write the dual of a constrained optimization problem. Okay, and the primal form we considered was something like this, as always, where you try to minimize a function subject to some inequalities, some equalities, and also you have x in some set x. So this x, this capital X, could be taken as the domain, or if you have some other inequalities which you want to handle separately, you can move it to that. Okay, and so we saw that the dual is a related problem. And like in the case of linear programs, what we were trying to do is get a lower bound. And the tool that we had here was the Lagrangian function. Okay, and we saw that the Lagrangian function for any set of multipliers for like lambdas and mu's, where lambdas are greater than or equal to 0 and mu's unrestricted. For that case, the Lagrangian, if you take, it's always going to be a lower bound for every point. So at every x, the Lagrangian constructed in this manner is a lower bound. And so if you take the inf of the Lagrangian, that's also going to be a lower bound for the entire feasible set. Okay, so that brought us to the dual function, and which was defined. So this theta of lambda and mu. So the dual function is a function of these lambdas and mu's, and we represent it with theta. So this was how we defined the dual function. Okay, and so we were interested in finding the best lower bound to our original function, and so here there was some variability we had in terms of lambdas and mu's. So this is something we could choose, and so the dual problem was to find the lambdas and mu's such that this dual function, this theta of lambda mu, is maximized. Okay, and we called this as d star, the value of the dual, the optimum value of the dual. Okay, and this is called the Lagrangian dual, and there are different variants of the dual. In particular, this is one of the most popularly used dual concepts, and we are going to look at that. Okay, and then I was telling you about this geometric interpretation of the dual, and there are some things I just wanted to clear up here. So what we did was we were trying to look at an alternate space. Okay, so we took an example where we had just one inequality constraint. Okay, and that was gx less than or equal to 0. And the Lagrangian was written in this manner, fx plus lambda gx. And so what we did is we looked at an alternate space where we collect all the points in this set x, and we look at all the possible values that gx and fx can take. Okay, so that gives us a two-dimensional set. Okay, so z1, z2, and so this g is what we use to represent that, and that's a subset of R2. Okay, and so we saw that this set had an important role to play, and in fact, the primal, you could write it entirely in terms of this set. So that the primal problem boils down to just minimizing z2 such that z1 is less than or equal to 0, and subject to z1, z2 in G. And similarly, the dual also could be reformulated in a manner involving just the z1s and z2s. So we were trying to see what the dual function meant here with respect to this geometry. So then we started off by seeing this, what is the z2 plus lambda 1 z1. So if you fix a value of lambda 1, and if you look at all possible values of z1 and z2, such that z2 plus lambda and z1 is c1, then what you get is the equation of a line. Okay, and in particular, it has a slope of minus lambda 1, and the intercept is c1. Okay, so that's what we drew here, and that c1 is actually what is coming up in the objective function of the dual. Okay, in the dual space. So you can think of it as something you're trying to do with the intercepts. You're trying to maximize intercepts, something like the worst case. So what we looked at the dual function in particular was you're trying to get the minimum intercept. Okay, so this inf over all z1, z2 in G. So the dual function, what it did was you fixed a lambda, you fixed a slope, and then you were trying to see what is the minimum value that of the intercept that you can get. Okay, so some line like this, which gives an intercept somewhere here, that could not have been a minimum, because there is a line like this which gives an even lower value of the intercept. Okay, so in that sense, this dual function for a given value of theta, for a given value of lambda, this theta of lambda, what it's doing is it's trying to find the best line that supports the set G. So some line that touches the set G. It has to touch the set G, because something like this, for example, it's clearly not an inf, you can do better. And something of this form, this line here, that's also not an inf, because there is some other line here which gives a lower intercept. Okay, if there'll be some other points specifically that it passes through, which will give a lower intercept. Okay, so that was the interpretation of the dual function. And in terms of the primal space, what we had, so this is the place where there was a slight issue yesterday. So in terms of the primal, what we were trying to say is we were trying to minimize Z2 such that Z1 is less than or equal to 0. So this set G you take, and all the points in this set, so the ones in blue, the shaded ones in blue, the part of G, and which of them has the minimum value of Z2. Okay, so the mistake I made was that I just looked at everything on this line. Okay, so so that's not right. So what you need to do is you need to look at all the projections of this G onto this. So even something of this sort, that will also count. So the P star will be actually something a little lower here in this case. Okay, so something like this. So that was the issue that was there yesterday. Oops. Okay. Sorry. So I think I should. Okay, so this P star was actually this value. And in terms of the dual, what we are doing is we saw this thing about the intercepts. So for each slope you take, you will get some value of the worst intercept, right? This inf of z. So now you're trying to find what is the best value of the slope, which means what is the value of the slope, which so that this worst intercept that is there is as high up as possible. Okay, so that was a dual function. And in this case, perhaps it would be something a little, yeah, maybe something of this sort. So in essence, like you can always have some kind of a gap between the primal and the dual. So even, so this was the other example we took. And here, so the correction is here as well. The P star is not here, but it's a little lower. So this is the value of the P star you take. Okay, and there could be cases where the dual objective, the D star and P star could match. So for example, in something like this, if you fix lambda as 0, okay, and then if you try to find the line supporting this, so the set G is only like it goes in this manner, okay, but if you take a line of slope lambda equals 0, then what you get is something like this. Okay, so this will be theta of lambda, this intercept will be theta of lambda. And in fact, that's the best you can do, and that will match with P star. Okay, but there are examples where the P star and D star can be different, and that example is something like this, where the P star again here. Sorry, yeah. So again, P star here is this point, and so this is the best value out of everything where Z1 is less than 0. So this is Z1 and this is Z2. Okay, and in terms of the dual, the best dual value, maybe it was something like this. Okay, so one of these could be the dual because it has to support the set, and so this has to go below. Okay, so this would be the distance. So here there's a gap between the primal and dual. Okay, so that's the sort of geometric interpretation of the dual. Now you could also try to see what happens if you had one equality constraint instead of an inequality. Okay, so the only difference would be that instead of taking lambda is greater than or equal to 0, you would allow for all possible slopes. Okay, so just try to take some examples and see how that works out. Okay? So yeah, this is something I wanted to clarify. And then we moved on to this example where we were trying to compute the dual. Okay. And so before that, let me just ask, are there any questions about the geometric interpretation or anything about writing the dual? Okay, am I audible?
Yes, ma'am.
Okay. So were there any questions? It was clear? Okay.
No, ma'am. I mean, clear, ma'am.
Okay. Okay. Good. Yeah, I think Bhavna said it's clear. Okay. Good. So now just another point I wanted to, just make it more explicit. When we write the dual, so what you'll be given is some kind of function like this, right? Some optimization problem with some function and some, maybe some equalities, some inequalities, and you also have that x is in R2. Okay, so this is what is given. Now, in terms of this capital X, you're free to choose it the way you want. Okay, so all these x's are given as R2. So one option is you can take this x as R2 itself, and in which case you will have multipliers for each of these three inequalities. Okay, and then you need to proceed and write the dual. You follow this procedure that we discussed yesterday. Now, you have this flexibility in terms of choosing this x. So what we did yesterday was we took this whole region. So all these points, I mean, all these inequalities, x1 greater than or equal to 0 and x2 greater than or equal to 0, we kind of absorbed it into the set x. Okay, so we took x as this form, x1 greater than 0, x2 greater than or equal to 0. And so when we wrote the Lagrangian, we had we had the multipliers only for this constraint, and that was lambda, and that's how we proceeded. Okay, so in general, like, you have the flexibility, so you can, nothing prevents you from, maybe you can even choose, these two as your set of inequalities, and this x2 greater than or equal to 0 alone can be in your x, or you could even choose no constraints in your capital X. Okay, and so in that case, the dual function where you try to minimize the Lagrangian, if this is the set, like if x in R2, if that is your capital X that you take, that is going to be an unconstrained problem. Okay, so there is some flexibility here for us to write when we write the dual. Now, a thumb rule is, you generally choose your x in such a way that, this problem, the dual function, at least that you can compute easily. So if it is an inconstant problem, there are more chances that you can have some kind of closed form solution, right? And constraint in here into x gets harder and harder. Okay, so generally you put in some constraints like x1 greater than or equal to 0, x2 greater than or equal to 0. These are some constraints which typically are reasonable to handle. But again, this is not always, sometimes it's not going to work. Again, whatever we did yesterday may not work, in which case you have no alternative but, to choose all these three inequalities as your original constraints and x as just x in R2. Okay. So that's one thing I just wanted to point out. And we worked out this example of writing this dual. Okay, so I just wanted you guys to try this out as a homework, like what happens when you choose x as R2 and then when you have multipliers for all the constraints. Okay, so now we will just do one more example of this. So this is a modified version of that example there, which we did yesterday. So additionally, you have these constraints, x1 less than or equal to 1 and x2 less than or equal to 5. Okay, so in terms of the feasible region here, what's going to happen is you have x1 and x2, and the plane minus x1 minus x2 plus 4, that is still the same. So you have this region, this is 4 and this is 4. So basically everything on this side. Okay, so that is the first part. And additionally, you have x1 between 0 and 1. So something like this. Okay, so yeah, so this part is what is feasible as far as x1 is concerned. And as far as x2 is concerned, you have everything between 1 and 5. Okay, so it cuts here. Okay, and what you have is basically this kind of a trapezium. Okay, so this is the feasible region, and you're asked to minimize x1 square plus x2 subject to x1 and x2 lying in this. Okay, so now again, you expect that your optimal will lie on this part because your contours look like this. Okay, and as you go away, as you go away from the origin, it gets the objective increases. So maybe some point here is what you would take. Okay, but we need to find out what that is. So let's just go ahead. We'll just write the dual first. Okay, so what I will do is here again I will consider the set x as x in R2 subject to 0 less than or equal to x1 less than or equal to 1 and 1 less than or equal to x2 less than or equal to 5. Okay, this is what I'll consider. And so I'll again have a Lagrange multiplier corresponding to this one constraint. Okay, so what is the Lagrangian going to be? Can somebody tell me what's the Lagrangian?
Minus lambda x1 minus lambda x2 plus 4 lambda.
So minus lambda x1. So sorry, it's lambda times. So there's no minus. So lambda times x1 minus x2 plus 4. Yes. Plus something, right? Was it Rohit?
Yes, ma'am.
Okay, so I think I didn't hear you. So can you say that again?
Hello?
Yeah, Rohit, am I audible?
Yes, ma'am.
Okay.
Plus f of x. So x1 square plus x2.
Yes, plus x1 square plus 2. I think my intent is also a little bad. So, okay. Anyway, so now this is the Lagrangian. Okay, and what I'm going to do is we need to find inf of L x lambda subject to x1 between 0 and 1 and x2 between 1 and 5. Okay, so this is going to be theta. Okay, so now let's just try to run this. I'll just write some terms.
Ma'am, your voice is
So maybe
breaking up.
Oh, is it?
Maybe it's just
Okay.
for me. Is anyone getting the same problem?
Yes, it was breaking a bit for me also.
Oh, okay. Don't know if there's something else I could use. Just a second. Huh?
It's back.
It's back. So just a second. I think I'll just switch to another connection.
Ma'am, I think you're still unmuted.
Oh, okay. Okay. Sorry about that. Am I audible?
Yes, ma'am.
Okay, so I just joined back in with another connection, so I hope this stays on. Okay, so so I don't know till where you heard me. So yeah, so so we were looking at this problem, okay, and Okay, I think I'll just share it. Yeah, thanks for seeing. Okay, is it visible now?
Yes, ma'am.
Yes, ma'am.
Okay, so yeah, I don't know till where you heard whatever I was saying, but anyway, the problem was to look at this one with some more constraints added. It's a modified version of the problem we saw yesterday. Okay, and what I said is I'm going to take this set X as this way, okay, where I'm going to also include these constraints x1 less than or equal to 1 and x2 less than or equal to 5 here. Okay, so there's just one Lagrange multiplier and I write the Lagrangian, and what I want to solve is the minimum of this problem subject to these constraints, infimum of the Lagrangian subject to these constraints. So what I'll do is I'm just going to group. So again, like what we saw yesterday, there is some amount of separability in terms of the function here. It separates out with respect to x1 and x2. So let me just group the terms in that way. So what I'll get is I need to find the infimum. So over this function x1 square minus lambda x1, and there's another part x2 square minus lambda x2, okay, plus 4 lambda. Okay, I need to find the infimum over again these constraints, x1 between 0 and 1 and x2 between 0 and 5. I mean, sorry, 1 and 5. Okay, so if we try to do the same approach we did yesterday. So yesterday how we did was we only had x1 greater than or equal to 0 and x2 greater than or equal to 0. So what we did was we ignored those constraints and tried to find the unconstrained minimum of this. And it turned out that that minimum was also feasible. Okay, so let's just see the same thing. If we do it here, so there are two functions here. I mean, I need to minimize these two. For a given value of lambda, there are two separate parts, and each of these I need to minimize. This is a constant. So I'll just call this function f1 of x1, and I'll call this f2 of x2. Okay, so in terms of f1 of x1, so let's just see what happens. Like what does this function look like? Okay, so so this function, if I try to plot it, like lambda is fixed, and how it would look like is for x1 is 0, the function takes a value 0. So this is f1 and this is x1, and now at the point lambda by 2, okay, it takes there is something going on there. Okay, so because the gradient is 0, so if I take f1 of x1 is x1 square minus lambda x1, so the gradient of f1, this is 0 at x1 is lambda by 2. Okay, so so something is going on here, and you will also see that this function is convex. Okay, in terms of x1, because the second derivative f dash f double prime, okay, this is always greater than 0. So this is actually exactly equal to 2, and it's greater than 0. So what you will get is some shape like this. Okay, so it takes a minimum at this point. Okay, and after this point, the function is going to increase. So you can see it in terms of the gradient. So f prime of x1, so this function f1, if I take the gradient, what I'm going to get is 2x1 minus lambda. So when x1 is less than lambda by 2, this gradient is negative. It becomes 0 at lambda by 2. And after lambda by 2, it's going to increase. So this is the shape I get. And of course, I can say that it's minimum at lambda by 2. But you also have this constraint, right? 0 less than or x1 less than x1 less than or equal to 1. So now x1 star equal to lambda by 2, this work only provided lambda by 2 is in your interval. So if 0 is less than so of course, so if lambda by 2 is less than or equal to 1, and of course it's greater than 0, that's given. So if this is the case, then you will lambda by 2 is the minimum. Okay, but suppose x1 is suppose lambda by 2 is to the right of 1. Okay, so in this case, the minimum would be this point 1 itself. Okay, so this if lambda by 2 is greater than 1. Okay, so in terms of this f1 of x1 star, so this is just x1 square minus lambda x1. Okay, so this is just going to give you, so what's it going to give you? Like if you take between 0 and, so this is essentially lambda lying between 2 and 0, right? So what is the value going to be?
Between 0 and 1.
Between
Oh,
0
f
and
of.
1.
So that
Yeah,
would be x1 star.
yeah. So it's, you just need to substitute this value. So it's just lambda square by 4 minus something, right? Minus lambda square by
Lambda
2,
square.
right? So this is just going to give you minus lambda square by 4. Okay. Now if you take lambda as greater than 2, what you will get is just 1 minus lambda. Okay. So that is this part of the function. Okay, are there any still this point? I know this, it's been going, but yeah, just stop, okay, if something doesn't make sense. Okay, so this is in terms of f1. Now you need to do the same thing for f2 as well. So let me just start a new page. So f2 of x, it's again the same function, x2 squared lambda x2. And this you're trying to minimize in the range 1 less than x2, 1 less than or equal to x2 less than or equal to 5. Okay, so again the function will look the same. So you have x2 and f2 here, and exactly the same function. So this is the value lambda by 2. Now you need to see whether this lambda by 2 lies in the range 1 to 5 or not. Okay, so suppose it lies in the range between 1 and 5. So then x2 star is just lambda by 2. So if 1 less than or equal to lambda by 2 less than or equal to 5. Okay, so now if x2 lies, I mean, if, so let's say this is 5. Okay, so this lambda by 2 lies outside this range. Okay, so 1 to 5 is and lambda by 2 is outside. So then in that case, what is the minimum value? What is the x2 which minimizes this function?
5.
5, right? So this is the case if lambda by 2 is greater than 5. Now you have also the other case when suppose lambda by 2 is on this side. Okay, so 1 is here and 5 is somewhere here. Okay, so in this case, what is the minimum value of the function?
1.
So you're 1, right? So you're looking at only this interval. So in this case, it's 1 if lambda by 2 is less than 1. So now in terms of f2 of x2 star, what you're going to get is, if you just plug this back in, so when lambda is between 2, so this first condition, so what you will get is this value
Minus
is
lambda square by 4.
minus lambda by 4. And now if lambda is greater than 10, what do you get?
25 minus 5 lambda.
25 minus 5 lambda, right? Now if lambda is less than 2,
1 minus lambda.
1 minus lambda. Okay, so this is the second part you get. Now in terms of the dual function, this theta of lambda, you need to combine all these pieces. So let's just do that. So theta of lambda, so there is already a constant here, like there's a 4 lambda, so let's just write that. So it's 4 lambda plus some f1 and f2. It's a sum of f1 and f2. Consider all these ranges. So you look at this function and this f1. Okay, so in the between 0 and 2, f1 is minus lambda square by 4. Okay, what happened? Okay, so f1 is minus lambda square by 4, So now we are looking at 0 less than or equal to lambda less than 2. Okay, so yeah, F1 is, and what was F2? F2 is now this value, right? 1 minus lambda. Okay, so you will get a set of intervals, so one between 0 and 2. Now, as per this function, about 2, everything is going to give you, I mean, the value is just 1 lambda, but here you need to distinguish again between 2 and 10 as well. Okay, so so now let's just take between 2 less than or equal to lambda less than or equal to 10. So 4 lambda remains, and in terms of F2, what are you going to get? Sorry, in terms of F1, what are you going to get?
1 minus lambda.
1 minus lambda. And F2 is going to be what?
Minus lambda square by 4.
Minus lambda square by 4, right? So in this range between 0 and 10, you're going to get the same value. And for lambda greater than 10, right? So the 4 lambda is still there. Plus, in terms of F1, you'll get 1 minus lambda, right? And F2 will give
25 minus 5 lambda.
25 minus 5 lambda. Okay, so this is the dual function, and you can simplify it further. So this is just going to be minus lambda square by 4 plus 3 lambda plus 1 whenever lambda is less than or equal to 10. Okay, and for lambda about 10, what you're going to get is what's the value? 26 minus 2 lambda, right? Right?
Yes.
Okay, so this is the function. So this is theta of lambda. And you see that it's again a one-dimensional function. And what you need to do is you want to maximize theta of lambda over lambda greater than or equal to 0, okay, in this range. So, I've just plotted it here for simplicity. Okay, so you can solve this graphically. So the first part, the one in red, I've plotted the quadratic function. So it's this quadratic function till lambda is 10. Okay, so till this point, it's the red function. So we are only interested in positive values. So from 0 onwards till 10, it's the red curve, and after x is 10, it's going to be the blue curve. Okay, so that's the function, and you can see that the maximum is attained somewhere here. And it turns out that the maximum, so it belongs to this red part, and it turns out that the maximum is attained at lambda is equal to 6. Okay, so here, so if you try to maximize theta lambda such that lambda is greater than or equal to 0, what you will get is lambda is equal to 6. Okay, the optimum value is lambda is equal to 6, and the value of theta of lambda star, the optimum objective here, what's it going to be?
Minus 9 plus 18 plus 1. That's minus 10. Oh, no, plus 10.
So plus 10. Okay, I'll just take it from you. So yeah, so this is what this is the dual, and this is going to be the dual solution. Okay. Now, I mean, you can also relate it to finding the primal solution. And in this case, actually, it will turn out that the primal and the dual values will match. Okay, so I'll just leave that as an exercise for you to find out. Like now you know how to apply the KKT conditions and solve this problem. So yeah, but this was primarily an exercise on writing the dual. So yeah, there are multiple steps that you need to follow to write the dual. And many times, like for each problem, there'll be something in the structure that you can make use of to write the dual. Okay, so yeah, so there's one procedure, but in order to simplify it further, sometimes you need to make use of something about the problem. Okay, so I hope this example is clear to all of you. Are there any questions on this problem?
No.
Good. So can I also hear from some of the others? Is this clear to you all? Any questions? Clear? Okay. All right. So, okay. Cool. So now this is one example. Now we'll just take this example of linear, maybe one more examples before I wanted to cover linear programs as well. Now, one thing to note is, these are examples where, the dual you got as a nice form. You got it as a closed form result. I mean, maybe in terms of just one variable, this was a piecewise function, but you were able to simplify the dual and write it in one compact form. Okay, but turns out that it may not always be possible. And sometimes your x variables might also show up in the dual for some cases. An example is this. Okay, so here there's just one constraint, it's just in one variable. Okay, so if we try to write the Lagrangian, what you're going to get is e power x plus lambda times x square minus 1. Okay, and there's no other restrictions on x. So the set x that we are taking here is just r. Okay, so in terms of the dual function, this is just going to be inf over x in r, e power x plus lambda times x square minus 1. Okay, so this is an unconstrained problem. Now you can take the gradient. So let's just take the gradient. So theta, so it's not theta of lambda, right? So this function. So this is another function. So if I take the gradient of this function, what I'm going to get is e power x plus 2 lambda x is 0. Okay, so let me just call this function f tilde of x. Okay, it's lambda is given, so I'm just calling it as f tilde. So this gradient of f tilde x, so this is just e power x plus 2 lambda x, and in minimizing it, you're trying to find the one with gradient equal to 0. Now further, if you take the second derivative of this, you're again going to get e power x plus 2 lambda. Okay, and this is greater than 0. Okay, always, because our implicit assumption is that the lambda we get here is going to be greater than 0, and e power x is anyway greater than 0. Okay, so this is actually a convex function, and if you find an x such that this condition is satisfied, that's going to minimize this theta of lambda. Okay, sorry, not theta of lambda, it's going to minimize f tilde. Okay, so the dual function, so let's just write the value. So theta of lambda is this thing here. So theta of lambda is just going to give you, like, you need to make a substitution here. So e power x plus lambda x square minus 1. Okay, so this is the case if e power x plus lambda x square minus lambda. So let's just look at this value. So suppose your lambda, so this is a function of lambda, right? So if lambda is greater than 0, then it's going to be this. But if lambda is equal to 0, if lambda is equal to 0 here, you're trying to minimize e power x. Okay, so this term goes off. And what you're left with is, x is unrestricted. So it can become arbitrarily small. So e power, it can go to minus infinity. And in that case, this will be equal to 0. Okay, so theta of lambda is one of these two, and this is the one which is more interesting. It's a dominating term than 0. So what the dual you're going to get would be maximize e power x plus lambda x square minus lambda. But of course, subject to these constraints, this x has to satisfy this, because that is the one which minimizes this function, minimizes the Lagrangian. So it also needs to satisfy that e power x plus 2 lambda x is equal to 0. And you are also taking lambda is greater than 0. So this is this case. Okay, so the dual is actually just this. And so here the variables are x as well as lambda. Okay, so you solve this problem, and if it is taking a value greater than 0, then of course it's this. It's the max of this optimization problem's objective value and 0. Max of this and 0 is what the dual objective is going to be. Okay, so yeah, so this is just to illustrate that sometimes your dual will involve the primal variables also. It's not that you will always get a separable form, like a nice form which includes only the dual variables. Okay. So I will just move on to another example of linear programs. So we've seen a dual earlier. I mean, we saw it with a different approach of writing the dual. Now let's write it in terms of whatever Lagrangian dual that we have seen so far. Okay. So what I will do here is I'm just taking the same problem that we originally wrote the dual for. So minimize C transpose X such that AX greater than or equal to B and X greater than or equal to 0. So what this would boil down to is, I'll just write the constraints in a little more detail. So this would be AJ transpose X greater than or equal to BJ for there are m such constraints. Okay, and I have Xi's greater than or equal to 0, and there are n such variables, and X in Rn, X is in Rn. Okay. So to bring it in the form that we want, we want everything in terms of less than or equal to signs, right? So I'll just write it that way. So I need to multiply both with the negative sign. So this is going to be the problem. So let me take the set X as Rn itself. Okay. So I will have to have Lagrangian multipliers for both these constraints. Okay, so you could do even the other way, like you could include x's in your x less than minus x less than 0, that also can be included in x. Okay, so you should try that out later. So for now, let's just take that, these have multipliers lambda j's, and these constraints have multipliers, let me call it tau i's. Okay, so the Lagrangian will be a function of x, lambda, and tau. Okay, so can you tell me what it is? So this is actually CIXI.
Summation CIXI.
Yes.
That's lambda j plus summation lambda j.
Lambda j times, you have this constraint, right? Minus, so you'll get Pj minus Aj transpose X, right? And so Aj is a vector, of course, and then you have
Tau
plus, tau I times, so minus tau I xi. Okay, so this is the Lagrangian, and I'm going to minimize this. So what you need to do is inf of this Lagrangian over all x, and this is an unconstrained problem. Okay, so here, let me just group these terms in a particular way. So this is inf over x, and I'm just going to group it based on the xi's. Okay, so if I take each I, so the coefficients of xi would be ci, and from this term I'll get a minus tau I. Okay, and from this term here, what I'm going to get, so this term here is just, so each of the aj's is a vector, so this is actually going to be aji times xi. Okay, each of this aj transpose x is going to be of this form. Okay, so if I group it in terms of the xi's, what I'm going to get here is ci minus tau I minus summation lambda, summation over all the j's, lambda j's, aj's. Okay, so this times xi. So just let me just write it a little properly. So this is summation over all i's, xi times, this is the coefficient you'll get for the x's. Okay, and plus there is a summation over j, lambda j, bj. So this is over the m constraints, and again like this. Okay, So this is an unconstrained optimization problem. So note that, if, whenever the Ci minus this term, if it's taking a value greater than 0, if for any of the i's, if this term takes a value greater than 0, then what I can do is I can set xi, to as small as I want. So this will go to infinity. Okay, it will go to negative infinity. And if this term is positive for any of the i's, then what I can do, if it is positive, I can set xi to be very small. If it is negative, I can set xi to be very large. Okay, so what happens is, if you want to have a meaningful bound, you must have this term is 0. Okay, for every I, if this term is 0, Ci minus tau I minus this term here. So if this whole coefficients of xi becomes 0, then this whole term vanishes and you're left with summation lambda j bj. Okay, so let's just write that. So this is going to give you lambda j bj, j equals 1 to m, if Ci minus sigma lambda j aj I, j equals 1 to m, minus tau I is equal to 0. Okay, and if not, this is going to take a value of negative infinity. So it's unbounded basically. Okay, so otherwise it's going to be minus infinity. So what we are interested in is the maximum value. So this is the value of theta of lambda tau. Okay, and now you want to maximize this quantity. So what it becomes, the dual would just be maximize summation lambda j bj. Okay, so this is just lambda transpose b in vectorized form, subject to these constraints. Okay, so Ci minus summation lambda j aj minus tau I equal to 0, and lambdas are all greater than 0, taus are greater than 0. Okay. Now one more thing you can simplify is the Ci minus lambda j aj. So this is true for all I. Okay, and so if taus are all greater than 0, you can completely eliminate this variable. This is the only place it occurs. So you could instead write these constraints as Ci minus summation lambda j aj is greater than or equal to 0. Okay, and so you can eliminate the tau variables completely, and your dual would be like this: maximize lambda transpose b. Okay, and in fact, this constraint, so you can see that this will work out to C minus A transpose lambda is greater than or equal to 0 in vectorized form. Okay, because A is this matrix, and if you say, you can work this out later, but this is what it's going to be. So this is in fact the dual that we saw, right? So maximize. So we had these multipliers. So at that point we called it some y's. So here we're calling it lambdas. We multiplied each of these with these lambdas, and then we had that B transpose lambda was a lower bound. And in order to have that lower bound, we said A transpose lambda should be less than or equal to C. So that's exactly what we're doing here. So A transpose lambda is less than or equal to C. And because these were all inequalities, we multiplied each of them with a non-negative quantity that was lambda. Okay, so that's why you have lambdas are greater than or equal to 0. Okay, so turns out whatever we derived earlier was indeed the Lagrangian dual. Okay, so you can go back and also check for other forms, for other LP forms, like how you would have checked with the other method. You can also try to write the Lagrangian. Okay, so try to write the Lagrangian with taking the set X as Rn. Now you can also try, taking the set X with these constraints. So then you won't have these tau variables, and then you can see what happens here. I mean, it will show up as a constrained optimization, but yeah, you can go ahead and see what happens there too. Okay, so these are all the different things you can try out for a problem. Okay, so are there any questions so far? Is it too confusing, or is it like, I don't know. I mean, the class is very quiet, so Is it all good?
The algebra part was visualizing and knowing which operations to perform to sort of break this into, like, visualize this as graph or whatever. Those steps were a little complicated, and like, if I am given a function, I don't think so I'll be able to do all of this, but maybe with practice or something.
Yeah. So yeah, definitely it needs practice. I mean, it's not like immediately you see it and you get it. So try different kind of problems, and it's also about choosing. Your some. I mean, the same thing. Like go back and try with. If you. I mean, with this itself, there were different pieces to the function. Okay. Now, if you had your x, I mean, you just took it as an unconstrained problem, that would simplify things to some extent. But then you would have like multiple variables, right? I mean, for each of these constraints. So it's kind of a trade off, like you make the right selection, and yeah, it requires a lot of care. And these steps you could make mistakes at. I mean, it's very easy to go wrong in these steps. So yeah, as you keep trying, as you try more problems, these things, it will come to you naturally. Okay, so yeah, I think, yeah, that goes without anything. So practice makes perfect. Okay, so
Yes, sir.
right. Okay, so how are the others doing? Can I hear from some more people? Harsimran, how has it been? Is it okay?
Ma'am, it has been okay. I'll need to go through the material again in some time to fully get it.
Okay. Okay. So if it's the algebra alone, like, yeah, it's fine. But I hope the procedure is clear, right? Like how I mean, the overall procedure to write the dual, like, I mean, at each level, like when you do this, when you compute the dual function, there is some algebra there that you have to, of course, figure out. But otherwise, it's clear, right? The overall method, like how you write the dual. Are there any questions at that part?
No questions, ma'am.
Okay. Okay. So I wanted to do another example of QPs. So maybe I will do this in the next time. So QPs, and I also wanted to discuss some properties of this dual function and some special cases in convex optimization. So yeah, probably I'll do these things in the next class. So yeah, we'll stop here and we'll meet again on Tuesday at 9 a.m. So I'll hang back for a while if there are any questions. Otherwise, thanks a lot for coming.
Thank you, ma'am.